Hey, in this video, we're going to cover waves and the explanations of kind of what they are. So let's dive in. So basically, when you see the wave, it looks like a particular shape on the oscillator, or whenever you're talking about waves as a vocabulary association, they have names. And the reason why they have the names is because they look like a particular shape. And the reason why they have a particular shape is when you're looking at the wave itself, it actually is a reference to a graph, a mathematical graph. Kind of like that. And on this side, you have amp, which is how loud the signal is. And on this side, you have frequency. So basically, there's the volume of it and the pitch of it, right? A sine wave is the most basic of all sounds that occur naturally in nature. And essentially, the frequency and the amplitude go all the way up, and they go all the way down as the sound dissipates, right? Through space and through resistance. So a sine wave looks kind of like this, right? It's very smooth. It has no breaks. It just, it goes there's no interruption in the sound. It's just a basic wave, right? Then we have a triangle wave. A triangle wave, the amplitude spikes, the amplitude and the frequency spike and then drop. So it goes up and then it goes down, right? And it kind of looks like a mountain. It, instead of very naturally peaking up and then going down, there's a sharp spike. As soon as it reaches its highest point in amp and frequency, it drops immediately, right? And then, and then you have a square wave. A square wave is essentially a wave that even more dramatically spikes in amplitude and in frequency. And whenever the waves are modified, typically it's usually through a filter. A filter is something that cuts off the frequency of the wave. And so the reason why you have such a sharp spike in your wave is because your filter is making it from this in the grander scheme, and then it's just going, it's cutting that off in a way so that it spikes rather than just being smooth. And a square wave, essentially in frequency and amplitude, is kind of at a 0 point, and then it goes up, and then it goes, right, the frequency and the amplitude are cut off dramatically once it peaks. And when it's done peaking, it essentially comes back down, right? So it goes about its business. It spikes in frequency and amplitude. It stays at that point, and then it drops down, and then it continues, right? Okay. Then the last, well, not the last, but the next one is a pulse width modulation oscillator. So a pulse width adjustment modulator would be, or an oscillator rather, it's essentially a square wave that you can adjust the length. So it's a square wave which you can adjust how long or how short this peak is, or, you know, both ways. So you can make it back into a square wave, or you can move it out and make it longer and make it sound dramatically different. The last oscillator, I guess, that I'll talk about is the noise oscillator. A noise oscillator is essentially is an oscillator that has no pattern in frequency and amplitude. So it kind of looks like this, right? It's completely random, right? Where it goes, what it's doing, how it behaves, and you know, when you think of white noise on a TV, that's essentially a white noise or noise oscillator. That's the basic overview of waves, kind of why they're the shapes that they are and what they mean. Yeah. So I hope that clears things up. This is important for the types of sounds that you're trying to generate. You know, if you want smoother sounds, then you go with a sine wave. If you want sharper tones, also there's the low frequency oscillator. I guess I'll go over LFOs too while we're here. So what is an LFO? Well, an LFO is it stands for low frequency oscillator, and essentially what it does is it modulates the behavior of a pre-existing wave. So, right, let's say you have a sine wave. So it kind of looks like this, right? Or actually, you know, forget that. This might make more sense if we use a triangle wave. Let's say a triangle wave, right? A series of triangle waves going over and over. You know, granted, and they're not, like, let's say they're all the same amplitude and all the same, like, you know, essentially, if we were to use a sine or an LFO, we choose what kind of oscillator it is. So it could be a triangle, it could be a square, it could be, it could be sort of depending on the synth, it could be a variety of things. If it was, say, a sine wave or a sine low frequency oscillator, it would basically essentially even out the peaks and kind of shape and smooth things out. So it would add a little bit, and it would basically, instead of it being sharp now, the low frequency oscillator smooths it out with its own modulation. That's the easiest way for me to describe it. So it kind of takes a pre-existing wave and changes the characteristics of the peaks of those waves. That's essentially what an LFO does. It has more of a modulation characteristic. This is the absolute basics of waveforms. If you want a more detailed explanation, get Welch's Synthesizer Cookbook. It's a really good book. It describes this stuff way better than I can because I am not a sound engineer. But also the other book that I read that has a lot of the same overlapping information in great detail is a book called Refining Sound. And that's that's written by a professor as a coursework book for a school in Texas for their sound engineering program. And it's really good. I hope this was useful. So see you later.